In this video we'll look at the equations of motion. The equations of motion are three equations which can be used to link time, displacement, initial velocity, final velocity and acceleration for an object with a constant acceleration. These will usually be in a straight line, but we do need to take account of direction involving opposite directions, so positive and negative directions will be important. So there's our definition for all those quantities, short form of them. And there's a formula that we're used to for acceleration, but as I've already mentioned, at higher this is usually rearranged into this form here, v equals u plus at, and that is the first equation of motion. We now look at the second equation of motion, and we consider when an object is accelerating. So we're looking at Nat 5, we looked at the idea that the only way you could get the distance travelled was doing area under graph. So we're going to take that idea at higher and just take the general idea an object is accelerating from u to v in some time t. So we're not filling in exact values here, we're using the algebraic quantities. But the same idea applies, that we can work out the displacement as the area under the graph. So we would split that into a rectangle and a triangle as normal. And the area of the rectangle would be its height, which is u, and its length, which is t. So it would be ut. And the area of the triangle, well, it's also got a length of t, but its height is v minus u. So its area is a half brackets v minus u times t. And notice this would simplify if there's no acceleration just to s equals ut, it would just be the rectangle bit. And we can simplify this further if we use the fact, they display this a slightly different way from what I would, but if we use the fact that v minus u is equal to at, then you can write this as a half times a times t squared, this term. What they've done in here is to add a t term to the top and the bottom, so you can recognise the v minus u over t bit in there to give you the a. But we then get the second equation of motion, s equals ut plus a half at squared. Now that might seem something that from the start you say, I would have no idea how to get there. But I think an important thing is that you're given the equations of motion, so you know where you're heading. So you can, because you've got a good idea of where you're going, it should hopefully make a bit more sense of how to get there. And I think that's even more true in the third equation of motion. We derive it by taking the first equation of motion. So I'll tell you at this point, the third equation of motion is v squared equals u squared plus 2as. Basically it allows us to link the other variables without the time being involved. So to get that, we take the first equation of motion and we square both sides. So that gives us v squared equals u plus at all squared. And then if we break out the brackets, the first term gives us u squared. The cross term, if you're used to calling it that in maths, would be uat, and there'd be two of those cross terms, so that's 2uat. And squaring the final term would give us a squared t squared. And then if we recognise that what we're aiming for, remember, is v squared equals u squared plus 2as, what we can do is take out a 2a from these two terms. So we've got the v squared bit, we've got the u squared bit, but the second two terms on the right hand side are not quite in the form that we want. So if we take a common factor of 2a out of the first one, that leaves us the ut bit, which is the first part inside the brackets. We don't have a 2a in the second term, but we have an a. So if we take out one of those a's and put an extra half term inside the bracket, which cancels out the two that's outside the bracket, then you can see that that would work back to the same. The second term would be 2a times a half a t squared, which would be a squared t squared. And hey presto, we should recognise now that this bit in the brackets is the second equation of motion, s, and we're proving where we knew we were going to end up anyway.